Welcome to Notes 9-2, Essential Skill Z2. Geometric sequences and series. This is the second part of Essential Skill Z2. It also includes arithmetic sequences and series from last time. Geometric sequences are similar in a lot of ways. They're kind of an upgraded version of arithmetic sequences. They have, each term is given by multiplying a constant by the preceding term instead of adding it. And we're going to call it the common ratio instead of the common difference. It's important to be able to look at a sequence and be able to tell whether it's arithmetic, geometric, or neither. To do that, we look at the common differences to see if there is one, and we look at the common ratios to see if there is one. Feel free to pause and try it before I finish. Our next task, similar to what we did with arithmetic sequences, is to find a formula for the nth term in a geometric sequence. We start with an example that we'll extrapolate a formula from. The formula we can extrapolate is we're going to take the first term times the common ratio raised to a power that's one less than the term number we're looking for. Again, we can solve problems involving the nth term through algebra or just plugging in. Our next task, of course, is to look at what happens when we add them all together. A geometric series is a sum, in the same way that an arithmetic series is a sum of the terms of a sequence. And again, we'll be dealing with partial sums if we only add up part of a series. We can use the same guidelines to write these in sigma notation. All we need is the nth term expression to put on the right of the sigma. Notice again, since n is the index variable, we leave it in the form of a variable. We do not replace it with 10. Our formula for a partial sum is a bit more complex than the others, but you'll see why in a moment. Let's see why that is. We're going to use a similar form of algebraic trickery to get a formula. First, notice how we've written the first partial sum. We have term 1. This is another way of writing term 2. If you look at the nth term formula, that's an expression for term 2. Similarly, here's term 3 and term n. That looks exactly like the nth term formula, as it should. If we take all of these terms and multiply by r, look what happens. Using a method similar to what we did with arithmetic series, we're going to combine these two equations. This time we're going to subtract them, and what we're going to find is a large number of terms drop out. First, let me make a slight adjustment so that we have all of the like terms lined up. Now when I subtract, it's important to note that the ellipsis contains a lot of terms. There will be a term on top that matches T1 R cubed. That one's going away. There will be a term on the bottom that matches T1 R to the n minus 1. This is all we're left with. Two terms in that difference, and we don't have to deal with that pesky ellipsis. Now we simplify and solve for s. And there's our formula. We can use this in the example we saw above. It is extremely important to notice that the r to the n will include any minus signs. Next, we're going to look at what happens with a geometric series that doesn't end. An infinite geometric series can have a finite sum. We're going to investigate this question in this example. This is clearly geometric. The common ratio is 1/2. Take a moment to read through this. Let's look at partial sums. The sum of the first term is just 1. The sum of the first two terms, I'm going to use mixed numbers because they're going to make the pattern a little more clear. Note that for subsequent sums, I can start with the second partial sum and simply add the third term in. That will give me the sum of the first three terms. Notice that these sums never reach 2. They seem to get closer and closer to 2, but they never get there. In other words, 2 is its limiting value. This is called a convergent series because these sums, the progressive partial sums, converge on 2. We can also say, and we will say, that 2 is the limit of the sum. That brings us to the definition. Our definition of the sum of an infinite series is actually the limit of the partial sums of the series. It does require that the partial sums do converge. Not all of them will. This one did. But that's why we need the language. If the partial sums converge, then the infinite sum is the limit of the partial sums. How do we know whether the series converges or not? There's a simple test. If the absolute value of the common ratio is less than 1. Let's take a closer look at that. It turns out there's a very simple formula for the sum of an infinite geometric series. Again, we have the condition on the common ratio. That's the only way this works. But if we have that, then the limit is simply this. Again, this deserves a closer look. Let's see why that is. What I'm going to do is expand S sub n to show the partial sum formula that we saw on the other page. To take the example from before, just plug in some numbers. I want to focus in on this piece, 1/2 to the n. N is getting larger and larger, so 1/2 to the power of n is going to get very, very small. If you think about it, this is going to go 1/2, 1/4, 1/8, 1/16. 1 over 2 to the 10th is 1 over 1024. We're getting very small fractions here. As n gets bigger, 1/2 to the n tends towards 0. That means for very large values of n, like when we take the limit of an infinite sum, this is effectively 0. Removing that from the formula leaves us with the simplified infinite sum formula from above. Since we're dealing with large values of n, we can treat that 1/2 to the n as a 0. This simplification hinges on the fact that r to the n tends towards 0. If it goes to 0, we treat it as 0. When n gets close to infinity. Typo, sorry. Fixed. Our question is, when does r to the n approach 0? Well, when it's fractional and less than 1. If we raise, let's say, 9/10 to a very large power, we're multiplying 9/10 times 9/10 times 9/10. That number eventually gets very small, and it will approach 0. The same holds true if it's a negative value, between -1 and 0. This fraction whose magnitude is less than 1. Another way to write this is with the absolute value. Take a look at these examples. What remains in this notes is another set of practice problems. It's very important to work these on your own. Please try them out. You have answers available so you can verify yourself.